Okay, this is problem number 20 from the force and motion test. It's a little ambiguous, so let's go through it. It says a spring with a spring constant of 55 newtons per meter is compressed to 70 centimeters or zero point 0.7 meters. An object with a mass of 3 kilograms is attached to the end of the compressed spring. So let's just, I don't know, we'll just put box. Oh, shoot. Typed it in the wrong spot. Now I want a cool box. There we go. That'll work. It's got to be transparent. Oh, let's do it like this. All right. I'll make it a little bigger. Cool. So there's a couple of assumptions. This is why I say it's ambiguous. There's a couple of assumptions that we need to make. One of the assumptions is that this is on a frictionless surface, okay, because it doesn't say anything about gravity or mass or anything like that. It doesn't say that it's horizontal either, but this spring is compressed. So it's going to exert a force this way. This is the force of the spring. It's compressed, so it wants to expand. It wants to reach its free length. Well, what is its free length? I don't know exactly, but I know that it's compressed 0.7 meters, right? That's a pretty long distance, okay? And what they really want to know is what is the acceleration of the object? Well, if the object is standing still while it's compressed, we're freezing this in a moment in time. So somehow we compress the spring and then we're going to release it. So the first thing I need to do is calculate the force of the spring. So I'm going to say the force of the spring is equal to the negative times the constant times the displacement, which is x. So the force exerted by the spring, the compressed spring, is going to be negative 55 55, not 50. Times 0.7. So the force exerted by the spring is about negative 38.5. Right? So in this particular case, this will be the negative direction. Okay. All right. So then we got to figure out the acceleration. Well, remember that the acceleration is based on the mass of the object. In other words, the acceleration is equal to the force, the force is equal to the mass times the acceleration. So when this gives loose, when it becomes an unbalanced force, we're gonna, the energy is conserved. There's a transfer of energy. So when I do the math, I'm just going to take the force. In this particular case, the force is negative and I got to think about how I want to word this. So when I do this, these two will cancel. And I get that the acceleration is equal to the force divided by the mass. And we'll do that in a second. But I got to come back to this formula here. The force exerted, we're going to have, so we have to decide what's positive and what's negative. Technically what we can do, and this goes back to your notes, we can call this negative, and that makes this positive. Because it's going to exert a force. We want the right to be positive, and we want the left to be negative. Essentially, our acceleration has to go in the same direction. So when we compress it, our displacement is technically in the negative direction. Okay? So technically that's a -7. So I wanted to, and it doesn't matter, it's just that the answer is a positive acceleration, and this is negative. So remember to put the negative here. So anyways, the force then is a positive 38.5 newtons divided by the mass, which is 3 kilograms. And that means that our acceleration is about 12.8 meters per second squared. Okay. Does that make sense? Technically, this is -7. All right. Yeah. Sorry, I hope I didn't confuse you guys. We could do it the other way. If we chose to do it the other way, we would have a negative acceleration, which would be the same direction as the compression. I think this is the better way to do it. Unfortunately, the solution from the textbook doesn't consider our displacement going in the negative direction.